Hi, everyone. In this talk, we will cover our state-of-the-art report on advances in neural rendering. This work is a collaboration between several researchers across many different organizations. I am Ayush Tewari, and I will briefly introduce you to our topic. Neural rendering, as you can guess, is closely related to traditional rendering in computer graphics. In traditional rendering, we create imagery of a scene with controllable 3D parameters, such as camera pose, lighting in the scene, or geometry and materials of the different objects in the scene. Neural rendering also aims to generate photorealistic images of a scene with the same set of 3D controllable parameters. However, instead of directly taking these 3D parameters as inputs, neural rendering methods learn to generate images directly from some input observations of a scene. For example, on the left, neural radiance fields can take images of a scene from different viewpoints as input, and after training of a neural network, this method can synthesize images of the scene from any unseen camera viewpoint as well. On the right, NERD takes images of an object as input and learns how to render new images of the object from novel viewpoints, as well as under unseen light conditions. So to summarize, the goal of neural rendering is to generate controllable and photorealistic images of real-world scenes. Neural rendering is new, but it's also a very active area of research. There was another STAR report on this topic 2 years back, which focused on 2D neural rendering methods. These methods use 2D convolutional neural networks, and these networks take some two-dimensional inputs, which could be some intermediate renderings computed using classic computer graphics methods. The CNN converts these inputs into the final rendered images, and this network is trained on real-world images. This report, in contrast, focuses on what we call 3D neural rendering, and the approaches covered here rely on a tighter integration of classic rendering methods and neural networks. These methods use neural networks to represent properties of the scene in 3D, such as the geometry and appearance, and then rely on a known analytic renderer from computer graphics to generate the final image. This renderer needs to be differentiable, such that the neural network can be trained using gradient-based optimization. The general trend in the field is to use more knowledge from physics-based light transport as inductive biases for neural rendering. As I mentioned, this is a very fast evolving field, and this talk aims to provide an overview of the field, but it does not include some of the very recent papers or papers which are beyond the scope defined in our report. We will cover several topics in our talk. We will talk about the fundamentals of neural rendering and also discuss several applications such as novel view synthesis, rendering dynamic content, and relighting. Finally, we will discuss some open challenges, and we will be happy to take questions after the talk. With that, let's start with the fundamentals. Hope you have fun.
Hi, my name is Ifan. Now I'm going to walk you through the fundamentals of neural rendering. But first, I think it's important to go back to the root and review the classical rendering from a vantage point. In classic rendering, we basically have two pillars: a 3D scene representation describing the properties of the scene, and a rendering engine which maps these given properties to the RGB values on an image. In the classic 3D scene representation part, we have information about the geometry, which can have various representation forms, such as voxels and points, and many others, as you see in this graph. And also importantly, we need to also store the texture and material of the object, which can have a profound impact on the appearance of the scene. And for realistic rendering, we also need to model the light sources. Now, on the other end, the image formation end, the graphics community has dedicated significant effort to develop efficient and realistic rendering engines. They can be primarily divided into rasterization and ray tracing. Rasterization is based on projection and is widely adopted in real-time rendering applications such as games. And on the other hand, ray tracing, it models the physics of the light transport. So it can produce very realistic images, but is very expensive computationally. Now, having this two-pillar classic rendering in mind, we can now move to the neural rendering. The first kind of work you will see through this talk basically harness the power of neural rendering to get a learnable image formation, which transfers the given scene representation to a realistic looking image. And because the input is usually already transferred to the image plane, some examples you see here are depth map, point clouds, projected point clouds, or semantic maps. We refer to this type of neural rendering as 2D neural rendering. And then we also have 3D neural rendering. It approximates the 3D scene representation this time with neural networks. And importantly, the rendering engine must be differentiable to propagate the gradient to optimize the neural networks. The enhanced representational power of these neural networks can offset the need for very complex and expensive rendering engines. In both scenarios, neural network serves as a fundamental function approximator, which can learn to move points, deform meshes, or approximate surface properties, and even approximate the image formation function itself. Now we can move to some concrete examples of neural rendering. And I'm going to walk you through some examples based on the different geometry representations. And first, let's have a look at point clouds. Points are usually represented with their 3D Euclidean coordinates. They do not usually have a radius defined in the world coordinates, but rather they do in scene space. And notably, the sparse density can easily lead to holes. This is why most approaches use neural features for each point that are then translated by a post-processing 2D neural network to the final image. So point representation adopt rasterization for the image formation step. But classic rasterization is not differentiable. And a popular approach to make differentiable point rasterizer is to soft blend the points both in the image plane and also in the depth. Most implementations use a hardness parameter in the blending function to modulate the spatial extent of this blending. And typically, a softer blending is used at the beginning of an optimization to allow global gradient flow. And then the harder blending can be used to allow fine-grained changes. Points can also be represented as spheres. The Pulsar renderer here, again, adopts a soft blending function, and it can render millions of spheres through very efficient and optimized implementation. The work by Ifan et al. Provides an alternative to soft blending. It approximates the rasterization function as a linear function. Therefore, it creates a long-range gradient without the need for hardness parameters. Now let's move to the meshes representation. Meshes, by having a connectivity information, can model surfaces quite efficiently. And vertex positions and textures can be represented now by the neural network. Here, Tato et al. Proposed the first differentiable mesh rasterizer, which makes it possible to modify mesh geometry and texture from 2D silhouette and 2D images. The soft blending technique we have seen previously in the point representation can also be applied now to meshes. For example, soft rasterizer use the distance to triangle edges to create this soft boundary, as you can see in this graph here. Instead of storing texture as vertex attributes, one can also leverage an existing UV map to learn a 2D texture map. In this example, learned neural features are stored in 2D grid. For a novel view, the texture map are then sampled according to the fixed UV mapping. and then transferred to the RGB images through a 2D neural network. The aforementioned scene representations, such as point clouds and meshes, they're all explicit, which means we can directly reference the surface elements. In contrast, implicit surfaces represent the surface as a level set of a function. And one commonly used function is called sign distance function. For every position in the 3D Euclidean space, it gives the Euclidean distance to a watertight manifold, and the sign indicates whether the position is inside or outside the shape. And the sign distance function is approximated using neural network. An obvious advantage of the representation is that it's continuous with respect to the 3D coordinates. The way to render implicit function is ray tracing. For every pixel in the image plane, one would shoot at a ray and find the surface intersection. Then another network, usually referred to as texture network, would take the coordinates from the intersecting points as input and then output RGB values. Besides the intersecting points coordinates, we can also additionally use the normals as input to the texture network. By the way, the normals are can be easily derived from the SDF. The texture network can be seen as the approximation of the bidirectional reflectance distribution function, BRDF, which is universally used in classic rendering. And it describes the interaction between incoming light with the surface. Now, this allows modeling more challenging lighting conditions and high reflectance surfaces. The surface intersection points are found by sphere tracing, which marches along the ray by a distance given by the sign distance function. Or sometimes people also use bracketing methods such as bisection, which iteratively confine the interval based on the sign of the probing points. In practice, usually a combination of both methods are used to efficiently and robustly find the intersecting points. Okay, with that, I think we can move on to discrete volumetric rendering before I give the stage to Ben to talk about the continuous volumetric rendering representation. Previously, in surface rendering, we have the basic assumption that the color of a pixel can be fully explained by light bouncing on solid surfaces. Before volumetric rendering, we would start to consider the volume as a medium where absorption, emission, and even scattering of light can occur. The properties of this medium can be approximated by neural networks and stored as neural features in discretized grids. One can then use Trillier interpolation to get the neural features for any point in the bounding volume. And to render a pixel, one would first aggregate the features of all the sample points along the ray, then convert the aggregated feature through a 2D neural network to the RGB values. And besides the static properties of the volume, we can also model the dynamic of the scene, such as this work by Lombardi and colleagues, which used a warping network to represent the shape variation in time. Now I will pass it to Ben, who will continue to talk about volumetric representation, but in its continuous form, and also cover the rendering of it.
Hi, I'm Ben Mildenhall, and I'll be giving an overview of view synthesis methods for static scenes. First of all, what is view synthesis? We'll start with a stack of images of a particular scene, and we assume it's possible to calculate corresponding camera poses for each image, so we'll know the camera's position and orientation in space, as well as any intrinsic parameters such as focal length. Given this sort of input data, our job is to devise an algorithm that produces a 3D representation of the underlying scene that's capable of rendering new views of the scene from any camera position within reasonable limits. Here we're just showing a fixed novel trajectory, but the actual use case for this would be a user controlling the camera with a mouse or gamepad, or maybe even by moving their head in a VR headset. There are a few basic design considerations when developing algorithms for view synthesis. The most important question is, what kind of input images are we going to get? Will they be taken under fixed lighting? Will the scene be static, or might some components be moving? Will we be able to compute accurate camera poses for this data? How big is the overall scene? Is it just an object, or maybe a whole room, or an entire city? And how densely captured will the images be? Will we have a very precise capture with thousands of well-calibrated pictures, or maybe just a few casual photos scraped from the internet? Our next consideration is particularly relevant in the new era of machine learning. We have two basic choices for how to reconstruct the scene. First is the standard machine learning paradigm. We assume we have a trained neural network that can take in the captured images and then spit out a scene representation that lets us do view synthesis. This type of network would have to be pre-trained over many captured scenes, probably by using a rendering loss on held-out test images and back-propagating through a differentiable renderer. This is in contrast to the second option of optimizing the representation for only a single captured scene. Here we don't require any large pre-training dataset, but the trade-off is that we'll need to do much more compute for every new scene we want to reconstruct. This is sometimes called overfitting or test time optimization to contrast it with the standard machine learning framework of training over a large dataset. Of course, here we are again relying on the differentiability of the rendering step. Finally, we'll have to choose a particular scene representation and renderer. These usually go hand in hand. The representation will be designed to work with a particular differentiable renderer. This choice is going to be based on what our overall view synthesis goals are. Do we want to render at very high quality and resolution, perhaps at the cost of slow render times, or would we rather have a method that can run in real time, maybe even on a low-powered device? To make these considerations concrete, let's consider NeRF. We'll walk through NeRF as one example of a static view synthesis method and then discuss some of the ways it's been extended and improved. So basic NeRF has very particular input requirements. The scene has to be completely static and bounded, the lighting can't change during capture, and it requires many input images, usually at least 100 for a full 360-degree object capture like this one. We optimize NeRF parameters from scratch on every new scene, using gradient descent on the rendering loss until NeRF reproduces all the input images accurately. And the underlying representation is a neural network that encodes the scene volumetrically. This results in very high quality and has a small memory footprint, but it's also very slow since you have to run the network many times to compute the color of each output pixel. To understand NeRF and other similar view synthesis techniques, it's important to go through some basics of volume rendering. Volume rendering has a very long history. Early papers by graphics luminaries like Blin and Kajia use the volume scattering equations derived earlier by physicists. These same ideas were later incorporated into rendering pipelines for volumetric medical scans, and the equations for alpha compositing and matting are also closely related. These days, any production renderer will have support for rendering complex volumetric effects, typically using fancy Monte Carlo methods to make this tractable. In machine learning, alpha compositing and volume rendering have become very popular view synthesis techniques over the last 5 years and are capable of producing some really nice results. The volumetric rendering model is particularly amenable to gradient-based optimization because it's smooth, in contrast to surface rendering, which has sharp discontinuities. Let's quickly go through this commonly used simplified volume rendering pipeline. We'll start by assuming we have some given 3D volume data. At each continuous point in space, we'll be able to query the volume to get both a volume density and a color value. And our goal is to render a 2D view of this volume from some camera pose. For each of the pixels, we'll have a corresponding 3D ray that's going to interact with the volume. However, we don't know ahead of time exactly where volume density is concentrated, so we have to sample many query points along the ray and compute volume parameters at each of them. Given that information, we can calculate the total ray color. To do that, we first estimate the opacity of the volume along each of the small segments, which is going to depend on volume density and the segment length. We then have to account for the fact that opacity in earlier segments closer to the camera can block color contributions from later segments. If you contribute alpha in one segment, you're going to decrease the contribution of later segments by 1 minus alpha. We combine these two factors to get a total weighted color contribution for each segment, and sum up over all the segments to get a color for the ray. Note that all of this is easily differentiable. This is just a smooth function of the underlying queried density and color values. So now we have a nice differentiable rendering model. Our question is, what underlying representation should we use to store that volume data? In NeRF, we use a fully connected neural network, often referred to as an MLP. At each point along the ray, we feed 3D position and 2D ray direction into that network and get out color and density values. Combined with volume rendering, this gives us a mapping directly from input rays to output colors. And we can use the training data given to us by all the input image pixels by taking them as ray color pairs and then optimizing our volumetric representation. This process lets us reconstruct the scene well enough to render novel views that were never trained on. So that's NeRF. It's quite simple and it can achieve nice results, but it's not at all efficient in terms of compute. And there's been a lot of subsequent work on making either the rendering process or that underlying representation more efficient. There's also work on relaxing the capture constraints to allow for more flexibility in real-world scenarios. I'll quickly touch on a few relevant papers, but please see the STAR report for more thorough coverage. One method for reducing the number of samples per ray is to use an acceleration structure from graphics to cull regions of empty space. In NSVF, a sparse voxel field indicates where the volume density is non-zero, and one only has to query the network in those particular regions. Alternatively, it's possible to combine volume rendering with surface-based representations like SDFs that can help us place samples only very near to the object boundaries while maintaining those optimization benefits that we got from the volume rendering model. In terms of reducing the required compute per volume sample query, one idea is to reduce the overall size of the neural network. This makes the network less expressive, but this can be counteracted by storing many varying local weights in smaller regions of space rather than one single global weight vector for the MLP. It's also possible to discretize the function learned by the network after training is complete, sampling it densely on a 3D grid, and then using that to render novel views much faster. And recent work has actually shown it's possible to achieve the same high quality results by directly optimizing an underlying voxel grid representation, rather than having to bake it out from a pre-trained network. One alternative to voxel grids is smoothly interpolated hash maps. This recently proposed idea is useful because it effectively allows for learned compression without requiring explicit sparsification. The representation is optimized for rendering quality, so hash collisions will automatically be resolved in a way that looks best in the resulting output images. This particular work also benefits from a very efficient GPU implementation, which means you can do near instant optimization of the underlying scene. This is a huge step forward from the 1 or 2 days required originally for NeRF. Moving on to robustness, one useful ability here is handling captures where photos are taken at different times, such as this dataset created by scraping tourist photos of landmarks. So these sorts of methods add additional variables to the underlying representation that can capture this appearance variation and render novel views under different lighting conditions. One other direction is to improve the handling of larger, unbounded real-world scenes with content far from the camera. Both of these methods use a parameterization of space that warps faraway coordinates into a bounded region before passing them into the network. We can reconstruct even larger scenes than that, though. For example, in block NeRF, many separate NeRF networks are tiled to reconstruct a full neighborhood of San Francisco, and city NeRF uses training data from many different scales and progressively activated positional encoding to have these sort of world scale scenes. One weak point shared by almost all view synthesis methods is that they rely on having accurately estimated input camera poses. So methods like NeRF and BARF will address this by simultaneously optimizing rendering loss for not only the scene representation, but also all of the input camera parameters. That was just a really quick overview of some recent work in novel view synthesis. Please see the full report for additional details on more methods and static view synthesis like these ones. And with that, I'll hand it over to the other presenters to address a few of these related areas. Thanks.
Hi, my name is Vincent, and I'll talk about how we can generalize across 3D screens or generalization for neural rendering. Okay, so as Ben has just told us, in general, the problem that we're trying to solve is that of given a set of images, we want to somehow fit a model to that set of images such that we can render novel views of the underlying 3D scene. That is also the problem that we're going to tackle in this case. So in general, the pipeline looks like this. We have a set of images. We have some kind of fitting or optimization that yields the parameters of our neural scene representation. And then we can render out the neural scene representation using our neural renderer. I'm going to generalize this notion of fitting or optimization a little bit and call it a kind of inference. And inference just means an algorithm that maps a set of observations to the parameters of our neural scene representation. Okay, let's look at the case that we have talked about so far, which is the case of overfitting. And overfitting means we have lots of images of a single scene. So for instance, consider this toy car here. We have lots of images, maybe 100 images of this little toy car. And in this case, let's say our scene representation was a neural field, like scene representation networks on NERF. We have a neural renderer like volumetric rendering or sphere tracing in the case of a signed distance function. And now inference in this case of overfitting is just fitting via gradient descent. So we're just going to render out an image of our neural scene representation, backpropagate through our neural renderer into our scene representation, and optimize the parameters to fit all of the images. And this is what this looks like for scene representation networks fitting a little toy car. And then a test time later, we can just render out novel views of the underlying 3D scene. Fantastic. And this, of course, gives rise to these fantastic photorealistic results. In the case where you have lots of images, you can fit the scene representation and then render it out from arbitrary perspectives, and that gives photorealistic results. Great. What if we only have a single observation, though? Let's say we only had a single observation of our toy car. If we try to do the same thing here, like we just backpropagate into our scene representation to fit that single image, even for the simple example of a toy car, we're just going to get garbage, right? So here, these are null views from the underlying 3D scene, and you can see that except for when the camera is really close to the training scene, the scene representation just yields garbage. Why is that? Well, the reason is that in this case, there is uncertainty in the underlying 3D scene. We have not observed all of the 3D points that we want to render at test time. And so we have to somehow fill in the information that we haven't observed. And that is similar to what you do. If I show you, for instance, this image of a bottle here, right? You can't see the backside of the bottle, but you have a belief over what the backside of this bottle actually looks like. And that belief we call a prior. And in this case, the inference algorithm, this thing that maps images to the parameters of our scene representation, has to be prior based. And so we need to learn from data how to reconstruct 3D scenes. And the general framework of this always looks the same. You have some kind of encoder. So this is our inference algorithm. It generally looks like an autoencoder. So you have an image, you encode it into a set of latent variables that we call Z. So this is just a set of learned low-dimensional latent variables. And then we have a decoder that takes these latent variables, uses it to parameterize our neural scene representation, and then we can render it out from arbitrary perspectives. And I'm now going to walk you through a few of the considerations that are at work here. So the first consideration is, imagine we already had a set of latent variables magically. How could we use them to actually parameterize or condition our neural scene representation? And this we call conditioning, and conditioning usually means making the scene representation dependent on the set of latent codes. Conditioning is actually very, very easy. The key insight is that any kind of conditioning for any kind of scene representation always breaks down to predicting some set of parameters of the underlying scene representation. In the case of neural fields. Or even in the case of voxel grids. Consider this example here. So we have a little voxel grid, and let's say we had a set of latent variables. One way this principle could be applied is saying you're going to predict some or all of the contents of these voxels with, for instance, a 3D convolutional neural network. Imagine you had a single latent code, you could just upsample it to the 3D voxel grid. And in that case, the whole voxel grid would be a function of the latent codes, and that would be an instantiation of conditioning this neural scene representation on the latent codes. Great. In the example of neural fields, there's seemingly more complexity, but it actually all breaks down to the same general principle. So for instance, let's say you could apply the same principle and just use a latent code to predict all of the parameters of your neural scene representation at once. So you just, and this we would call a hypernetwork. So you take a latent code, you have just a fully connected neural network that takes the latent code and just predicts all of the parameters of the scene representation. So this is what we used, for instance, in scene representation networks. And then there's this thing of conditioning via concatenation. So there you take your latent code, you concatenate it with the input coordinate, with the input to the neural network, and then that's how you condition the neural network. Seemingly, that is something different, but actually it turns out this is identical to predicting the biases of the first layer. So this is of the neural networks. This is actually identical to having a single linear layer that takes the latent code and maps it to the vector of biases of your neural field. And then lastly, there's something called film conditioning. And in that case, you predict, you take the latent code, and from the latent code, you predict a per layer, per neuron scale and bias. And this is, for instance, what's used in StyleGAN v3 or in PyGAN. And in this case, it's also quite intuitive. Again, you're predicting the scale and the bias of each of the layers. And more generally, you can always show that it's basically, it breaks down to predicting some of the parameters of the weight matrices and biases of the underlying neural network. And most papers these days actually choose film conditioning for conditioning. My experience is that a hypernetwork or a film network indeed works best, but your mileage may vary. Cool. The second question is local versus global conditioning. Do you want to and what does that mean? Again, you have latent variables and you have your neural scene representation. Global conditioning means that you have latent codes that do not vary with the spatial coordinate that you're interested in decoding right now. So imagine you had a query coordinate x, and you had your neural field that maps that coordinate x to for instance, the density and the color. Global conditioning would mean that irrespective of where you are, you always had the same latent code. So the latent code parameterizes the whole scene globally. In contrast to that is local conditioning. And in local conditioning, basically the latent code varies with the query coordinate. So in this case here, you have a query coordinate, you have some kind of other discrete data structure, and dependent on the query coordinate, you get a different latent code. And then you use that to locally condition your neural field. And this we call local conditioning. Global conditioning is, for instance, used in scene representation networks or differentiable volumetric rendering. It has the limitation of only parameterizing relatively simple scenes, but it does give you a latent space for the whole class of scenes that you're interested in. Local conditioning is, for instance, used in via pixel-aligned features in Pi4 and PixelNerve, where a 3D coordinate is projected onto the image plane and used to look up the feature there. And that allows you to generalize to compositional scenes. But you don't have a latent space per object. But this is a very popular approach these days. Interestingly, also a form of local conditioning is object-centric features. So imagine you have a scene representation per object in a compositional scene. Like imagine you have like something like Clever, and for each of these objects, you have a separate little object-centric representation. That is also a form of local conditioning, because depending on where you are, you want to use a different object-centric representation to decode that. And that is, for instance, used in URF at ICLR 2022, or this paper COLF that is going to appear in arXiv soon. Cool. Lastly, how do you infer the latent codes? In general, that is done via an encoder. So you have, for instance, an image, you use an encoder that outputs a latent code, and then that's what you use to condition. Or you can also do it via auto-decoding. And here the idea is that for each of your training samples, you have a set of latent codes, and you're jointly optimizing these latent codes together with the weights of your neural field or of your neural scene representation. We don't have time to go into depth, but this is basically the general two approaches. Okay, there's other forms of generalization as well, like gradient-based meta-learning, but we don't have time to go into depth here. And most recently, there's also interesting transformer-based decoders, which are also a different form of conditioning, worth taking a look, but we don't have time to talk about them here. Okay, so generally, generalization enables you to reconstruct 3D scenes from incomplete observations. I want to talk about one other interesting side effect, which is that when you generalize anyways, you can think about including other parts of this pipeline in your generalization as well. So for instance, you could think about, because neural rendering is expensive, also learning the rendering operator jointly with the whole rest of the model. This is what we proposed in this paper called light field networks, where basically instead of sampling lots of points along array, like in NERF or in scene representation networks, we instead parameterize a network that you take the whole ray and you just sample the whole ray from the neural field, and that just gives you the color that is observed by that ray. And why does that work? It is uniquely enabled by the generalization across scenes, because you're basically learning the rendering operator is what this boils down to. So instead of having a separate scene representation and a separate renderer, you're basically learning to infer a representation that is already rendered in a way. So this is more difficult, and it is limited to simple scenes in the case of global conditioning like here. But recently, progress has been made with transformer-based decoders that allows to fit also more complex scenes. So this is a very exciting line of work. So in general, I think there's this notion of doing computer graphics with neural scene representations, where the focus really is about how do we design neural renderers and how do we design the neural scene representation. Then there's the notion of vision. How do we go from images to the parameters of the scene representation? And I think there's really interesting questions along both of these lines. And one thing that is really exciting with generalization is to think about using this whole pipeline as a form of doing self-supervised learning, because it gives you a way to supervising this inference algorithm, which basically maps images to something that represents the underlying 3D scene. So this is really exciting. Thank you so much for listening, and have a great fun with the workshop.
Generative adversarial networks are an algorithm that pits two models against each other in an adversarial game. The generator's job is to take in random noise and create fake examples. The discriminator's job is to look at these fakes and look at the real examples drawn from the training dataset and determine which is which. Over the course of training, these models compete against each other, and they each become better and better at their respective tasks. The discriminator becomes an expert at identifying fakes, while the generator learns to produce high-quality forgeries that can fool the discriminator. The generator learns to map random vectors sampled from the distribution to distinct fakes capable of fooling the discriminator. The result of this training process is a model capable of creating endless and incredible forgeries. Here, we discuss 3D-aware generative models, a class of generative adversarial networks that creates 3D scenes but are trained from 2D images. For those familiar with 2D GANs, we think of image generation with a 3D-aware GAN as almost identical. The only difference is that instead of directly producing a 2D rendering, as is common with 2D GANs, we break the rendering process into two distinct components, 3D scene generation and neural rendering. Each training iteration, we generate a random 3D scene by conditioning a scene representation on a vector drawn from random noise. But we don't have multi-view images or ground truth to supervise the model. Instead, we select a random camera pose and render an image. We use our discriminator to critique the renderings and assign a realness score. By maximizing the judged realness of our renderings, we backpropagate through the pipeline and improve the realness of our generated 3D scenes. By indirectly supervising our generations with this discriminator, we don't require any 3D or multi-view ground truth. Meanwhile, our discriminator is trained as an image classifier. We supply it with real images from our training dataset, as well as recent renderings produced by our generator. We supervise it to correctly judge which images are real and which ones are fake. There are many reasons why you might be interested in 3D-aware generative models. Of course, simply having a generative model that operates in 3 dimensions holds enormous promise. The capability to quickly generate endless 3D fakes that can sometimes fool even humans has great potential. But another huge advantage of 3D-aware models is the capacity to learn 3D structure from unstructured image collections. Unlike most 3D vision algorithms, which rely on either 3D ground truth samples or posed multi-view images to provide direct supervision, the unsupervised nature of 3D-aware GANs enable training from unstructured image collections, which are far more easily obtainable. 3D-aware training removes one of the major obstacles to 3D vision, which is the lack of 3D data availability. Hologan was the first to demonstrate 3D-aware training using a 3D representation parameterized by voxel grids. Generative radiance fields replace the voxel grid of Hologan with a neural radiance field, inheriting better multi-view consistency. Pygan used sinusoidal activation functions and more powerful conditioning to enable generation of more finely detailed scenes. Recent methods have replaced density-based representations and rendering with surface-based methods, enabling more accurate recovery of scene geometry. Meanwhile, other methods have turned to CNN-based upsampling and refinement to sidestep the computation requirements of neural ray marching and enable higher resolution image synthesis. Still other approaches have transitioned from using large multi-layer perceptrons to efficient hybrid representations, which speed up neural rendering and open the door for real-time applications.
Rather than just generating new images, we can use a pre-trained 3D GAN to reconstruct existing images, a process typically referred to as GAN inversion. In naive GAN inversion, the generator network weights are frozen, and then we optimize for the latent code that most closely reconstructs the input image. This allows us to re-render the input image from novel viewpoints. Instead of having to optimize the latent code during inversion, Pix2Nerf jointly trains an encoder with the 3D GAN that learns the mapping between generated images and sample latent codes. During inversion, the input image is directly encoded to a latent code, which speeds up the reconstruction process. However, it is possible that the input image may not reside perfectly within the latent space of a pre-trained 3D GAN, which results in a noticeable visual gap between the input and reconstruction. EG3D uses pivotal tuning to perform GAN inversion in two stages. First, the generator weights are frozen, and the latent code that best reconstructs the input image is found, just like in naive GAN inversion. Then, the generator weights are fine-tuned to better recover the finer details for a more faithful reconstruction. Beyond novel view synthesis, image editing using GANs has also been explored. In the space of 2D GANs, many works perform image editing by traversing the latent space of a pre-trained 2D GAN. GAN space performs PCA on the latent space and walks along principal component directions to edit image attributes. Interface GAN computes attribute hyperplanes, and it walks along them to edit specific attributes. Finally, StyleFlow learns a continuous normalizing flow, which can be queried with an input image and a vector of desired image attributes. 3D GANs involve both geometry and texture, which may make the editing task a bit trickier to accomplish. Some editing works have proposed disentangling the generation of geometry and texture, such as SoftGAN. Here, specific semantics are edited by masking the generated texture while keeping the generated geometry the same. Similarly, FenNerf follows the same paradigm of disentangling geometry and texture, performing edits using a semantic mask proxy. Recent advances in 3D GANs, particularly in view consistency and image quality, have enabled editing and animation of images without requiring semantic masks or video training data. For example, one recent work leverages a pre-trained 3D GAN and animates an input image using GAN inversion. The method consists of expression encoding, 3D GAN inversion, and pose rendering. First, the expression of the target image frames are transferred onto the source image using a 3D morphable model. A pre-trained encoder network predicts a textured mesh that is manipulated using the detected expressions of the target video frames. Then, GAN inversion inpaints missing regions, such as the mouth. These images are then composited onto the original image and embedded into the GAN latent space. Finally, the pose predicted by the 3D morphable model encoder allows us to re-render the output at the correct pose. Although the latent space of a 3D GAN is more complex in that it must also encode geometry, Latent space attribute editing techniques for 2D GANs, such as style flow, can be naturally applied to 3D GANs as well. "3D GANs have seen dramatic improvement recently, but there remains a good number of problems to address. For example, the performance of a 3D GAN is strongly dependent on having accurate camera poses, which are currently typically estimated for each image. Campari demonstrates that jointly learning the camera pose with the 3D GAN results in better view consistency. Another interesting problem is the composition of scenes. Currently, most 3D GANs are trained on scenes with a single object, and the next logical extension would be to generate larger and more complicated scenes. Giraffe approaches this by parametrizing scenes as a composition of foreground object nerfs and a single background nerf. In summary, 3D GANs have many useful applications beyond generating new content. Some of these applications include novel view synthesis, editing, and animation of existing images.
Hello everyone, my name is Golyanik and we will next look at representing and rendering dynamic content. This part of the presentation is prepared by Tretschk and myself. The problem we want to look at takes as input a monocular RGB video of a general dynamic scene and is not restricted to faces or human bodies, as can be seen in this example. We then want to obtain a 4D reconstruction of that scene, namely the geometry, appearance and deformations. This reconstruction then allows us to synthesize novel views. Ideally, we want them to be consistent across space and time. What's difficult about this problem? Well, we need to accumulate the geometry and appearance information across time, but this leads to ambiguities. Even static scenes already exhibit ambiguities between geometry and appearance. For example, we could place a flat plane in front of each camera instead of learning a representation that is actually 3D. But with dynamic scenes, we now also encounter geometry changes like deformations and appearance changes like shadows. All of this can again be exploited by the optimization to avoid reconstructing a meaningful 3D scene across time, since we only have a single input view per time step, so this problem is even more under constraint than static reconstruction. We thus need to impose priors on the deformation modeling. For example, since we observe only a single view per time step, the deformation model needs to handle currently hidden geometry in order for novel view synthesis to give reasonable results. Furthermore, when parametrizing deformations, we also need to be able, for example, to introduce discontinuities into the model in order to handle topology changes. In the last couple of years, we saw a wave of nerve-based works coming out that made significant progress over previous attempt at the full problem setting. These mostly consider real monocular videos as input. There are also several other works that use slightly different input settings, like multi-view or time-of-flight sensors. So, how can we add deformations to nerve? Recall that nerve represents a 3D scene as a function that maps any 3D point to its opacity and color. This mapping is implemented by an MLP. Given a radiance field, we can specify a virtual camera and trace rays from it. We then employ volumetric rendering by sampling the radiance field along each ray and integrating the samples to obtain the final image. This formulation, however, only supports static scenes. If we want to capture dynamic scenes, we can additionally condition the radiance field on time. This entangles geometry and appearance with deformations. To disentangle deformations from geometry and appearance, we can represent the dynamic scene using a static canonical radiance field and a separate deformation field. We use space warping to deform the underlying canonical volume. Let's consider the same dynamic scene at two different time steps. Since the space warping has deformed the volume, we can render the deformed state using straight rays. This is the idea behind ray bending, but how is it realized in practice? We start with the straight rays. We then have to invert the space warping in order to access the geometry and appearance information in the canonical volume. That means that every point sampled along the straight ray needs to be mapped back to the canonical volume, thereby bending the ray. We can implement this as a ray bending function b that has the power to offset any point x prime along the ray to give a point x in the canonical volume. This function is conditioned on time t, which allows it to map all time steps into the same static volume. The ray bending is trained jointly with the canonical volume using a reconstruction loss similar to static nerve and additional regularization on the deformations. Let's see how these two deformation models compare. We have time conditioning and we have ray bending. The crucial difference between both are correspondences or temporal consistency. In the case of time conditioning, the correspondences are more of a soft constraint. They are modeled by an auxiliary 3D scene flow and they can drift over time. This allows time-conditioned methods to reconstruct frames rather individually, since incorrect correspondences across time are not too problematic. Thus, these methods can empirically handle larger motion. We can see this here. The input video on the left is rendered into novel views on the right. On the other hand, ray bending uses correspondences across time as a hard constraint. This is done via ray bending into a static canonical model. Thus, the correspondences cannot drift over time. This makes it difficult to recover from a wrong estimation of large motion that might occur early during training. Therefore, these methods empirically handle only smaller motion. Here, we see a scene that exhibits motion that is at the most complicated end of what the current ray bending methods seem to be able to handle. Another aspect are appearance changes like shadows or material. In the time conditioning framework, these are straightforward to model. The same holds for topology changes, as we can see again when looking at the bubbles in this novel view video. However, ray bending struggles with appearance changes, since the canonical model that contains the appearance is independent of time. These methods also have difficulties with the discontinuities required for topology changes. There are currently two classes of deformation models with complementary advantages: time conditioning and ray bending. Tear the extreme ends of a spectrum. Time conditioning treats every time step as a keyframe. Ray bending, on the other hand, uses only a single keyframe. We will hopefully see methods that fall somewhere in between in the future. We might also imagine a method that starts on the time conditioning end of the spectrum and anneals into a single keyframe over the course of training. Some limitations that should be lifted are, of course, the standard limitations of static nerve. It is slow, supports only a limited scene size, has no prior on how the scenes look like beyond observations, and so on. For dynamic nerve in particular, a number of methods currently use auxiliary inputs like camera extrinsics and intrinsics, background 3D points, foreground 2D segmentation, depth, optical flow, or instance segmentation. It would be nice to reduce the reliance on this, since they likely do not generalize well to difficult real-world scenes. And with that, I'd like to close by mentioning two other future directions, namely modeling physics and the ability to edit the representations. There are already a few examples in the discussed papers. For example, motion sculptures. We can also get some simple visual effects based on foreground removal, and we can exaggerate motion. Thank you very much for your attention.
Hi, my name is Thies, and I'm leading the Neural Capture and Synthesis group at the Max Planck Institute for Intelligent Systems in Tübingen. I want to give you a short overview of how you can model human faces and human bodies with neural representations. Note that in the following I will present work from my group. I refer to the state-of-the-art report for a variety of different approaches. All of the approaches are somewhat following the same principle. First, you need to have good face or body tracking. Then you can learn implicit, explicit, or volumetric representations around the reconstruction, inheriting the motion priors from the underlying face or body models. Thus, the resulting avatars can be controlled via the plane shape coefficients in the case of a face, or with the skeleton joint rotations in the case of the body. Let's have a look at some projects for human face and head modeling. When modeling human head avatars, we are often having the following setup. We have a monocular input sequence, which we use to reconstruct our avatar, which then can be controlled with our plane shapes to get new expressions. We can control the pose and the viewing direction. In this project, called NURFace, we actually represent the avatar with a dynamic neural radiance field. So this is very related to the NURF approach, but instead of having a static MLP, we have an MLP that is conditioned on the expression, so on the plane shape coefficients. So for each point that we sample along array, we evaluate the MLP with the plane shape coefficients. And there we get our color and density values. So this means that we basically have a dynamic neural radiance field. So the radiance field adjusts to the specific expression that we want to display. As you can see, we can achieve 3D consistent outputs here, which actually look much better than what we had before with the 2D approaches that do 2D neural rendering. Here's some additional example where my face avatar is controlled by Andre's face here. So this is a raw output, so we haven't filtered anything here, and you can actually see the positional encoding gives you multiple versions of myself. So that's what you see here on the left and right and also top. So these are repetitions from this sinus and cosine embeddings. But overall, the face region, which has been learned, looks quite sharp and follows the motion from the input. As you can see here on the right, the estimated normal and depth maps are actually quite noisy. So you will not get a really good reconstruction of the geometry with this approach. Follow-up approaches actually do a much better job in this. They actually represent the geometry not with a density field as we do here in this approach, but with an SDF. In case if you really want to have a precise geometry, which also has correspondence over time, you actually want to have some explicit representation. That's something that we did in this project called neural head avatars. So here the idea is that we have a neural network that predicts the vertices of a mesh. So the mesh has a constant topology, which stays constant over the entire sequence, and the geometry is adapted throughout the time. As I mentioned in the beginning, the first step is always to get a coarse estimate of the face. So this gives us the plane shape coefficients and a rough estimate of the shape of the person. Based on that, we can actually employ a geometry network which models the displacements from this space mesh to this fine detailed mesh. And this geometry network, which predicts these offsets, is conditioned by the model parameters that are optimized in the first step. On top of that, you can also employ a texture network, which gives you then the final appearance of your avatar. This avatar is also controllable. You can just apply the different plane shape coefficients and also the rotations of the jaw. And you can also use this for facial reenactment as shown here. When we compare the different approaches, you can see that this explicit representation actually gets much sharper details in the face region and is also more consistent throughout the time. Here you can see a variety of different faces. And the interesting thing is that you can also represent different types of hair. So also like the long hair here is recovered. So these two approaches that I just shown are either implicit or explicit. And exactly the same principles can be used for representing bodies. When reconstructing bodies, you can actually again have the two different styles of neural rendering. You can do a 2D neural rendering, as we did here in these projects, or you can do this also in 3D. So for 2D neural rendering, you can have these neural textures that are applied on top of the face or on top of the geometry of the body, which then looks like this. You can actually also extend this to a kind of 2.5D neural textures, where you actually have layers around the surface of the simple mesh, for example. One key aspect of getting nice results for bodies is having good tracking. And this is actually something that is not that easy. That's actually why we are concentrating on getting better tracking. In this project, Dynamic Surface Function Networks, we tried a much simpler case. We have an RGBD input, which actually allows us to get depth estimates. And based on that, we try to estimate the body parameters and the surface of the human. So this is our input here on the left, and our goal is to reconstruct the geometry such that we can later animate it. So to model the dynamic surfaces, which change over time, you get all the wrinkles and changing details. For that, we also use a neural network. So this neural network is similar to the MLP used in NERF, and we use positional encoding to encode a position on the simple surface, which is then fed into this MLP, which is conditioned on the pose, and this gives us this continuous offset surface, which can be applied to the simple model. And then you can use this to rasterize your geometry. You use differentiable rendering to optimize both the pose and the weights of this dynamic surface function network. And in the end, we can get results that look, for example, like this. So you can see that the wrinkles on the body are changing with the pose. This does not only work with high quality depth sensors, but also with the old Kinect sensor, which you can see here. So you get really all the details throughout the time. You can get all the wrinkles, and you can actually also see all these marker locations here, which are used in this sequence to evaluate the tracking accuracy. So this dynamic surface function network can actually also be extended to RGB. There are ongoing studies that show promising results. And with that, I want to conclude this session about digital humans in motion. And I also want to leave some advice. Like throughout all these projects that I did in this field, it's important that you are not religious about a specific representation and a specific method. It's also not about the training data that you have. You can use RGB, RGBD, whatever you want. In the end, it's about how we can actually solve a problem and how we can simplify problems to actually develop new methods such that we find a proper solution.
Hi, I'm Srinivasan, and I'll be talking about some relighting and material editing applications. As you've already seen in this tutorial, neural volumetric representations such as NERF are a very effective technique for representing objects in scenes, like this backyard here, in a manner that's easy to optimize from observed images. Current state-of-the-art NERF models, like MIP-NERF 360 shown here, are able to produce really beautiful photorealistic renderings and recover detailed scene geometry. However, NERF's representation is designed for reproducing the appearance of a scene exactly as it was captured, and does not provide a way to simulate how the scene would appear under different lighting conditions. Let's take a look at why this is the case, using this visualization of a toy scene that just consists of this colorful cloud. We can think of NERF as representing a scene as a continuous volume of particles that emit light. So we have an MLP F that outputs the volume density at any location x, and another MLP-G that outputs the color emitted by particles at that location, along any viewing direction, omega sub out. Rendering a ray that passes through a NERF is simple. You just sample points along the ray, and the final color is a sum of the light emitted by particles at each point, multiplied by how much that point is blocked by closer samples. But this representation does not give us a way to simulate how any point's appearance changes with new lighting conditions. To enable relighting, we first need to replace NERF's model of all points being emitters with a model where all our points have a scattering function, like a BRDF in the case of opaque surfaces, that describes how particles reflect or scatter incoming light. So in this model, we just have an MLP-F that outputs the volume density and parameters of the BRDF for any 3D location X. Then, we can simulate how the light from external sources is attenuated and reflected by particles in the scene. So this sounds simple enough, but it turns out that simulating the transport of light through this volumetric representation introduces a lot of computational complexity. Let's think about how we would compute the color of this camera ray, only considering direct lighting from point light sources. This means that we're considering the effects of emitted light, that is reflected by particles, along the camera ray towards the camera. We first have to query the network for the volume density at each point along the camera array to figure out how much each point is blocked by closer points. Then, for each point, we must compute the visibility between that point and each light source by densely querying the network for volume density along each light ray. So keep in mind that each of these dots represents a full evaluation of a neural network, and that we have to do this procedure for every ray in a training batch for roughly 1 million training iterations per scene. There's been a lot of recent research into recovering relightable neural scene representations, and one useful way to contextualize and compare these works is to think about how they propose to avoid this immense computational burden that comes with simulating the transport of light through the volumetric scene representation. I'm going to go over the strategies used in a few of the initial works in the space, but keep in mind that there's many more excellent papers in the subfield, so I encourage you to check out the full review paper for additional discussions. Let's start with this first strategy of using a specific lighting setup during capture that simplifies the computation. So this paper, Neural Reflectance Fields, was actually the first work that proposed extending NERF to enable relighting by using the MLP to predict parameters for a BRDF at any continuous point in space. Another one of the key insights in this paper is that since simulating relighting with arbitrary light environments can be very expensive during training, it can be much more efficient to use a capture setup with a co-located light and camera, which just means that there's a point light source located at the exact position of the camera. As we can see, in this case, the light ray samples we need to simulate the reflection of light off of particles in the volume actually coincide with the primary camera ray samples, so no extra computation or querying of MLP is needed during training. However, this strategy limits us to using data that's captured in labs with controlled lighting. So this next paper, called Neural Reflectance and Visibility Fields, builds upon neural reflectance fields and says, well, instead of completely avoiding sampling light rays by changing our training data, what if we just reduce the cost by approximating these visibility computations during training with a neural network that takes in a 3D point and direction and outputs the visibility of the surrounding environment along that corresponding ray? This paper in Neural Reflectance and Visibility Fields trains this visibility network along the network that represents scene geometry in order to make the predicted visibility consistent with the current geometry at any point during training. So in a NERV model, we have an MLP-F that outputs the volume density and BRDF at any location X, and another MLP-G that outputs the visibility of light coming from any direction omega sub n to the point X. This strategy lets NERV use images that are captured with more than a single point light source, and then efficiently render that new views under more complicated lighting at test time. Both of these works, and really all the works that decompose appearance into materials and lighting, also enable you to edit the scene materials after optimization. Another effective strategy that completely eliminates the need to sample the neural field along light rays is to use an analytic representation for lighting and reflectance. So two recent techniques, neural reflectance decomposition, or NERD, and PHI-SG, represent environment lighting and reflectance using spherical Gaussian functions. This enables the integral of lighting against reflection at any point to be computed efficiently without having to sample light rays. But it makes the assumption that there's no self-occlusions. So while the strategy is quite effective for modeling convex objects illuminated by an environment map, it has trouble simulating the effect of cast shadows. Another strategy to reduce computational complexity is to reduce the number of samples required along each primary ray from the camera. and this can be done by using a surface-based representation of the scene, such as a signed distance field like in PhiSG, or by simplifying volumetric geometry recovered by NeRF into a surface-like representation, as done in NeRF Factor. So NeRF Factor uses the geometry from a pre-trained NeRF to simplify the inverse rendering procedure by only considering a single surface intersection per ray. For any ray from the input training cameras, NeRF Factor computes its expected termination depth in the NeRF volume and assumes that the radiance along that ray is due to direct illumination from just that point. Furthermore, using pre-trained NeRF geometry lets NeRF Factor pre-compute the direct visibility to an external environment source in any direction from these surface intersection points. By using this pre-computed surface geometry and visibility, NeRF Factor then optimizes for a reflectance field and environment lighting, and is able to efficiently relight objects while also simulating visibility-based effects such as cast shadows. Finally, I want to briefly mention that a full lighting plus reflectance decomposition is not always necessary to enable some really cool editing effects. A paper called NewText trains the MLP surface parameterization that maps from 3D points in the scene to the unit sphere, as well as a texture function on that sphere, along with a NeRF model, so that the appearance of the scene is represented by a texture that can easily be swapped or edited, like in this example here. And RefNeRF also decomposes the scene into spatially varying reflectance map functions that enable separately editing diffuse and specular components of the appearance, such as making the specular appearance rougher or shinier, as shown on the left, or editing the diffuse color of the car, as shown on the right.
In this section of the talk, we will discuss several relevant engineering frameworks. Working with neurorendering models poses notable engineering challenges for practitioners. Large amounts of image and video data must be processed in a highly non-sequential manner, and the models often require differentiation of large and complex computational graphs. Developing efficient operators often requires working with low-level languages, which at the same time makes it harder to use automatic differentiation. We briefly touch on a few interesting engineering frameworks addressing some of these problems in this section. Sharded file formats are a great solution to the data storage and random iteration problem in many scenarios. Sharding means that a dataset is broken up into multiple pieces, the shards. Several of them can be read in parallel by multiple workers, with one worker per shard. Each worker can read its own shard sequentially, while a control process can query random workers when new data is required. This leads to a certain amount of randomness, while maintaining efficient sequential reads per worker. For each major deep learning framework, such a file format and surrounding infrastructure exists. For TensorFlow, the TF record format. For PyTorch, the web dataset format. NVIDIA also has proposed a high-performance storage framework, AI Store. Our next area of interest is experiment parameterization, a common problem for pretty much any ML workload. We identified two quite general software packages to mention here. Hydra offers a great way of parameterizing complex workflows. It can be used in easy yet powerful ways for reading configuration values from files, as well as from the command line automatically. Furthermore, it offers ways to tie configuration together with object-oriented design, and even adds automatic support for hyperparameter search. On this note, we also want to mention RayTune as a very general, very powerful toolbox for hyperparameter tuning that provides access to many algorithms. Now that we can load our data and parameterize experiments, we are ready to create neurorendering models, often with operators that are not part of the standard toolboxes, yet with high performance requirements. The differentiability of these operators is critical, meaning that automatic differentiation or auditive, or AD for short, is extremely helpful. Depending on the application, we might have to execute operators for large inputs. This is called macro AD. Or for many small inputs. This is called micro AD. Depending on the specific application and the structure of its computational graph, different frameworks might have advantages. Again, the list in the paper is slightly more extensive than here in the talk. Enzyme AD is a powerful AD package that allows to differentiate any function in C++ or CUDA. It is still early in its development, but quite powerful. Halide is another project for making vectorized image processing operations easily programmable in C++, with the ability to create CUDA kernels. diffTaichi provides a framework for differentiable operations with a focus on physical simulation. Enoki is the vectorization and differentiation framework of the Mitsuba 2 renderer. JAX is an autograd framework for Python and NumPy functions that is performant and versatile. JAX Nerf directly provides a Nerf implementation using JAX. Several frameworks that help specifically with creating rendering operations. NVIDIA Optics provides hardware-accelerated primitives and a framework for ray tracing. TAG is a differentiable programming language that has support for optimizing integrals with discontinuous integrands, with interesting potential applications in rendering. Several frameworks for rendering with more or less integration with deep learning frameworks and with different strengths and weaknesses exist. And lastly, we put together a short, incomplete list of some of them here.
Hello everyone, my name is Niessner, and it's the honor to present the final part of our neural rendering tutorial. And I'm going to talk about the open challenges in neural rendering, what I believe is going to be missing from a practical standpoint, but also very importantly from an academic standpoint. So if you're thinking, of course, there has been a lot of hype recently. There's many papers appearing at the computer vision and computer graphics conferences. But there's, of course, also a lot of papers being put on archive on a daily basis, and people who are working in the area know that it might even be sometimes quite stressful. But the big question is, where are we, and are we close to solving neural rendering? Are there still open problems or not? And in this context, I would like to start with real-world applications. So the question we also always have to keep in mind, why are we using neural rendering to begin with? Like, what are the end user applications at the end of the day, and where do we believe all the research we're doing around it might become useful and handy? And one of the big things, of course, in computer graphics that we're working towards is basically video games and movies. So if you're looking at video games right now, the question is, can we use anything in neural rendering on the research perspective? Can we use that yet in a video game? And the honest answer is it's way too slow. And I think, of course, when you're doing a research paper, right, you're happy that you can produce a video. But I think a lot of people don't realize how fast modern GPUs can actually rasterize polygons. So I tried this quickly out on my local machine here. It has a very old 1080 GTX. So it can actually rasterize about 2 to 3 million polygons in about 0.2, 0.3 milliseconds. And that's with a very basic implementation. I didn't optimize anything. There's no culling. It has some basic textures on it. So it's really, really fast. And this is it's a 5-6-year-old GPU right now, right? And we have to be pretty aware that in a video game, you are under serious time constraints. So typically, in a modern video game, you have, if you want to run it at 60 frames a second, right, which is what a lot of games are aiming for, you have about 16 milliseconds for a frame. And these 16 milliseconds, they're not going to be just used for some forward rasterization pass. There's going to be a lot of stuff going around it too, right? You have to basically figure out all the physics. You have to figure out a lot of extra stuff when you want to change the environment, like dynamics. There's a lot of user input stuff going on. possibly lighting and so on. So it's not just the rasterization, of course. So there's a lot of other stuff going on. So the rendering is typically being split up even in multiple render passes. You have a shadow pass and stuff like this. So maybe some of these things can be combined in a single pass with neural rendering, but you have to be still pretty much aware that you have pretty much for a forward pass, you don't have much more than a millisecond probably, or maybe 2 milliseconds in a game to render millions of polygons. And if you're comparing the rendering speeds what we have right now in neural rendering, we are far off from that. So we have made a lot of progress as a community, right? A lot of research papers have recently shown good progress, but we are far away from that. So if we're getting real time on a high-end GPU for a toy scene that is static without any changes and stuff like this, then we're happy for a research paper. But at this point, we are far away from the rendering speeds that we still need. So we don't see any adoption of neural rendering, I think, too much yet in video games, mainly because of the speed. In movies, it's a little bit different. In movies, we do see some adoption, like face replacement, for instance, has been done quite a bit. Post filters have been done a lot. Photoshop, actually, things like these, they're using some versions of neural rendering. So there's neural networks being used to apply the filters for sure, to apply some image edits, to improve quality, upsampling, and so on. It depends a little bit how broad we define neural rendering, but there are some applications where it's being used, but it's not yet the majority of everything, right? It's not like we can go and say, hey, we have like a script from an actor, and then we suddenly get a movie out of it. We're not quite there yet. It might happen, right? I mean, we see a lot of progress on NLP-based versions with combined with neural rendering, so maybe there's a way around it. And one of the part of the issues is basically what is the right hardware to deal with, right? So current GPUs, while they're great for training neural network, I mean, the hardware units there for rasterization, they're just really, really incredibly fast, as I just mentioned. So overall, I think real-world applications, since it's not being adopted that much yet, I think this is great for us researchers, meaning that there's a lot of things to work on. And I want to go into a few details here. One of the things that's probably the most discussed right now is what is the right representation. So do we need a neural representation? Basically, do we have MLPs that, for instance, store something like a radiance field in its kind of implicit structure? Or do we have explicit representations such as voxel grids, sparse voxel grids, and so on? And you could make an argument for either one of them. One of the reasons I think why neural rendering, for instance, in the context of radiance field became very popular because the tool chains of the optimization, like PyTorch, SGD optimizers, stuff like this, they're perfectly tailored to that. But nowadays you also see a lot of papers that actually use explicit grids, like Planoxus is a good example, and many related papers actually that use explicit data structures to do similar things what neural rendering did. So they're kind of going more into exploiting differentiable rendering pipelines. So maybe neural is not only the thing we should be looking at, but maybe we should put another emphasis on generally differentiable rendering or volumetric rendering in the context of classical data structures. And I think this is resurfacing quite a bit in this context. And I think that is quite an interesting research question. Like, you know, how much do you want to use a neural network for? How much do you want to use explicit data structures for? And my gut feeling is there's probably room for both. But what we have seen originally is that there was a lot of research with neural networks, of course, because that's how this whole field originated. But now there's a lot of people actually looking into how to make rendering pipelines differentiable and then trying similar optimizations that we used to do in neural networks with classical data structures. So I think that's quite an interesting question. And between those two, there's a lot of combinations, right? There's a lot of hybrid representations that use voxel grids maybe as a coarse data structure and then use MLPs in the nodes of the voxels. And this exists for static scenes, but it also exists for various dynamic types of scenes. Following up on that, maybe neural rendering is not just used for the rendering part, but maybe it could also be used in terms of the reconstruction. So typically when I'm giving a talk, I'm often motivating why do we need neural rendering. I'm going to tell people this is how computer vision looks like on the left-hand side, that's from the Kitty data set, and the right-hand side, this is how computer graphics look like. So how can we make computer vision look like computer graphics? So how can we do this reconstruction right? And maybe one part of the answer, what the right representation is maybe for the reconstruction, we need a neural representation, right? Maybe neural rendering can serve us very well in order to do multi-view stereo reconstructions. So for instance, when people ask me, what is NERF, right? And I'm always going to answer it's not really a learning method. It's more like a multi-view stereo reconstruction method that at the end of the day gets your radiance field that is going to be reconstructed. And then you can render it from different viewpoints. And I think that's kind of the idea maybe of neural rendering. It doesn't have to be used as a neural version in the end application, but maybe it's just being used for the reconstruction in order to solve the inverse graphics problem. And I think that is quite a powerful motivation probably for a lot of research in the future. And then maybe in the end application, you're still going to take this neural representation, and then you're going to convert it into explicit representation such that it can readily be consumed by modern GPUs, for instance. Another big challenge is controllability. So for instance, how do you edit these neural representations, right? So if you have hybrid representations, you have some control, but if you have a static room and you want to move stuff around in a post-process, that's pretty difficult. Whereas if you have a 3D mesh, it's very easy, right? You have a chair and you move it around. You just move the geometry around, and you have a scene graph you can apply. So, how do we realize a scene graph in an MLP-based representation? It's not so clear. So even for static scenes, this is really difficult. People have started now to use, for instance, object-based reconstructions and then use proxy geometries, which embed the neural representations, and that is maybe an idea. But then when we're talking about dynamics, it becomes even harder, right? Like if you're thinking about face reconstructions, also like how do you say, oh, you wanna make the mouth change in a certain way? Like this level of controllability is pretty much non-existent. So at this point, we're actually pretty happy if you can do reconstructions with dynamics, right? But even there, I think we're not quite there yet either. So if you're thinking about what are the dynamic null rendering papers, right? So there have been first steps, like NERF is a good example. This is one of the examples we see here on the left. We have seen methods that work on humans. We've seen methods that work on faces. And like NERF that does some small scale deformations during the capture. So the goal here was not really controllability, but rather like figuring out that our reconstruction, in this case from radiance field, doesn't fall apart, right? And I think we're really at the beginning when it comes to dynamics in larger scale environments, and I think we're nowhere close to having that one solved. And I think this really deserves a lot more research. Also, another thing what is interesting, often when people use proxy geometries, like humans in this case, or faces in the bottom right case, this was one of our papers actually. In these works, I think it is very it's mostly decoupled actually. So what you do first is you reconstruct the proxy geometry offline and then optimize the neural representation on top of it. But this joint optimization is often not there yet. So like dealing with dynamics, doing the end-to-end reconstruction there, it's still very much at the beginning. So I think that making this work in like real-world environments is still going to take quite a bit. I think another big question is generalization. So this is an example from one of our works. It basically it learns like null representations where the training samples only have single images as input, right? So this is like, it's kind of the opposite of classic NERF, where you say, oh, you're going to have multiple viewpoints, and from there you're going to reconstruct the radiance field. Whereas here, the idea is you only have a single image as input, and you kind of want to learn 3D structures via multiple instances, but each instance alone doesn't have any 3D information. And this is a question I think is also very interesting, right? Like, how do we make sure we don't just quote unquote overfit to one scene, but then can go ahead and actually generalize across scenes, leverage possible intermediate optimization results, or use like priors on dynamics, materials, and lighting across scenes, and actually help it to guide the reconstructions in under constrained settings. So I think generalization is actually a big challenge, generally speaking, when we're talking about null representations. When using an MLP, it's very difficult to generalize to begin with, right? Convolutions are much better there, but they have other disadvantages. So I think this is kind of a big open problem, I guess, not just for neural rendering itself, but for these kind of null representations as a whole. like how do we generalize across different samples, scenes in this case, and so on. And finally, I think a big question is how much can the neural part actually do? How much does it deviate from classical reconstructions, and how much do we need the neural part later on in the end-to-end rendering? So here's an example. This is from a work we did a while ago, where basically the idea is you're going to have neural pixels on top of a geometry. And the geometry in this case is very wrong. So you see this is just a cube. This is the proxy geometry, and with the neural renderer, which is essentially a 2D convnet, this neural texture is converted into an image. So you see this kind of 2D rendering, this neural rendering part in 2D here, is figuring out how to convert the wrong geometry with this kind of abstract neural representation on it into an image. But the geometry, of course, is wrong. We're still expecting few consistent results from it, and we're expecting some controllability from it. But it's far away from, right? It's not a good representation in a sense for this object, but the neural renderer is fixing it afterwards. So the big question is, where do we end up in this kind of in the setting? Like, how much does the neural part have to fix in the rendering when we didn't get a perfect reconstruction, for instance, or we have imperfect 3D representations? And how much does maybe the neural even help to get better reconstructions, what I said beforehand? So I think like this kind of interplay between computer graphics and learning tools and neural networks is kind of a very interesting point. I think it's actually not just neural networks that are interesting here. I think the differentiability of rendering pipelines is quite relevant, because it doesn't have to be a neural network, right? It can be a different representation too. So finally, I want to say, well, of course, until we have holograms, I think we're far away from neural rendering, right? Working in practice, I think practically speaking, we're actually just at the beginning. If you're pretty honest, I mean, yes, it is pretty hot right now in the research area, but this is a super young field, right? Like this is less than a few years old, basically. And we're still very much at the beginning of our research endeavor as a community. And I think we actually have just started. It's by no means clear where we're going to end up with. And it's very exciting, actually, because even in the short time frame that the community has started to work on it, there has been a lot of progress. And I expect this progress to continue. And I hope there will be many, many more exciting research works coming out in this area. With that, I would like to conclude. I would like to refer back to the state-of-the-art report. Of course, this was the work from a lot of research labs, right, from experts in the field here. And it's very good. I'm actually going to be physically at EUROGRAPHICS, so this will be also nice to catch up with a lot of people again. And with that, I would like to thank everybody for attending or watching the videos of the state-of-the-art report. I hope you are as excited as we are, and I hope also that there will be more cool research ideas coming out of it. Thank you very much, and hopefully see you in person at EUROGRAPHICS.